Let's take a little peeky pie at section 4.6, which is graphs and models of exponential data. You are definitely going to need a calculator for this one. Woo! So we will model exponential growth and decay scenarios. We started that in section 4.5, and now there's a little bit more. Interpret answers in the context of situations. We're going to be solving a little bit more in this one. Example 1, bacteria. There are 3 million bacteria at 11 a.m. and 1 bacterium divides into 2 bacteria every hour. Each one of them divides into 2. Reproduction. Fill in the table. Should we do this in millions then, I feel like? Let's, instead of calling this number of bacteria, let's call this either millions of bacteria or number of bacteria in millions. And then hours since 11. Okay, so at 11, 3 million. At noon, well, each one of them divided into 2. So there should be 6 million. Because every one now became 2, right? So everyone became 2. And so we have twice as many. Got it. And we have twice as many again because everyone becomes 2 again. So there's 12 million and then there's 24 million. That's a lot. Let's see. Yeah. Right. Okay. So, and just in terms of, yeah, we're good. Fill in the table. Done. Is this model linear, inversely related, or exponential? Oh yeah, this is definitely exponential because immediately, excuse me, I see that we have a doubling situation. Yeah. Constant multiplier, constant ratio of 6 divided by 3 is 2. 12 divided by 6 is 2. 24 divided by 12 is 2. So that constant ratio between 1 to the previous is the same amount. It's 2. Is this model linear, inversely related, exponential? How can you tell? A constant multiplier of times 2, which means that if you are repeatedly multiplying by 2, you need an exponent. Maybe I'll even write that. Repeated multiplication means exponents. Okay, maybe I could have written that over here. Write an equation that models this situation. Sure, absolutely. From the last section, we know that with exponentials, we have this kind of model, but I don't want to call it Y. That's ridiculous. We know what's going on. We have bacteria. I'm going to call that capital B for bacteria. Then millions of bacteria is equal to the initial. Okay, so maybe I'll write this. Initial constant multiplier, right, to the explanatory variable. Okay, where B was bacteria, the initial amount was 3 million, constant multiplier was 2, and time, hours. So maybe I'll call it H for hours. Okay, clearly indicate what each variable represents. So where B equals the millions of bacteria and H equals hours since 11 a.m. Lovely. Predict the number of bacteria that will be on the surface. Okay, this is on, these bacteria are on some surface, maybe a chair or a whatever, table. that will be on this surface at 11 a.m. the following day, assuming that no one cleans the surface and that there are no new bacteria put on there in addition. Okay, so here's what I'm thinking. So if there's no other changes, we're still following this pattern. And 11 a.m. to 11 a.m., right? 24 hours have passed. So H is given to us as 24, because that's hours since 11 a.m. previous day. And so that means we can compute. So the number of bacteria, so B equals, all right, let's see. We have 3 times 2 to the 24 power. So hundreds, thousands, millions, 50 million, 331,648 million of bacteria. Okay, so I'm going to take a brief little moment to talk about this, which is fine, but compare this back to section 1.7 where we talked about scientific notation, because this is a really large number. It's really large. And millions meant, let's see. So hundreds was 3 decimal places. Thousands was 3 more, so that makes 6. So 6 decimal places in addition to this, right? So there were really, hundreds, thousands, millions, right? 50 millions. So hundreds, thousands, that many millions of bacteria. So just to bring it back and label this out so that so this is the hundreds, right? This is thousands, 10,000s, 100,000s. This is millions. This was billions. And this is trillions. Okay, right? And 100 was 10 squared, 1,000 was 10 cubed. 10. So not that this is part of it, but it's a really large number. It's 50 trillion bacteria. And if we were going to write it in scientific notation, we would have to count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And in terms of what I just said with the trillions, you know, I was thinking of this in terms of 50 times 10 to the 12th, because 10 to the 12th is the trillions place, the single trillions place. But anyway, so just so that we're crystal clear, 50 times 10 to the 12th is 50 in terms of language. Okay. Wow. That's a large number. Okay. And I actually want to add a little tidbit to this one too, in terms of, let's suppose we had this really massive number and we were trying to figure out these hours. So, little dream. Okay. The undoing here of this on your calculator. So the undoing of this exponential is actually log. So I want to show it just so that you have some exposure for your future classes. So I'm going to go math, and then if we go log base, then here's what they're saying. The base is this doubling or the pattern. So this log base 2, and of this really massive number, so 50,331,648, right? And I hit, did I put it in right? Oh, darn it. I forgot about that 3. I had to get rid of the 3 first. Let me, so we had 3 times 2 raised to the 4th. 3 times 2 raised to the 24th. I did forget to undo this division by 3 first. So in this equation, I take that and divide by 3, and then I do this thing, log base B of that number, 16, so hundreds, thousands, 16,777,216. So I just wanted you to show you the undoing of this would be to first divide and then do log. That's what that's created for. Anyway, log undoes exponents. Okay. Well, looks like I'm going to have to start example 2 on the next video.